All right, so in this first example, the first step we had was to isolate the exponential expression. So here I have 2 to the x equals 61. So the exponential expression is this right here, this 2 to the x. It's already isolated. The next thing I need to do is rewrite it in logarithmic form. So remember, that's kind of the heart thing. So it's going to be log base 2 of 61 equals x. So I'm going to rewrite log base 2 of 61 equals x. And now this expression right here, the log base 2 of 61, I can put that into my calculator. And you can do that however you need to. If you have a graphing calculator, you can just type it in and it will go straight to the answer. If you do not have a graphing calculator, you need to use change of base. So you would type in log of 61 divided by log of 2. And either way, you'll get the same answer, which is that x is approximately, and I'm doing the squiggly equal sign because it's not exactly, because it's this huge long decimal. I'm just going to do 4 decimal places of it. So 5.9307 is going to be our answer. All right, for problem number 2, this one, the exponential expression is this right here, e to the y plus 3. It is not isolated because of that minus 6. So the first thing we have to do before we can put this into logarithmic form is get rid of that 6. So now I have e to the y plus 3 equals 30. Now I can put this into logarithmic form. Now remember that when you have something that has base e, so I have this, it would be e to the 30th equals y plus 3. But remember, because it's base e, I'm not going to write log base e of 30. I write natural log of 30 equals y plus 3. Okay, so now I'm going to get a decimal for the natural log of 30. That decimal is 3.4012, and you just get that by putting natural log of 30 into your calculator. There's an ln button right on the front. So I just rounded it to 4 decimal places, and that equals y plus 3. And then to get y totally by itself, I have to subtract 3 from both sides. So I have y now completely by itself, and my answer would be 0.4012. All right, this last example, my exponential expression is e to the 4x, so I have to get rid of this 5 before we can do anything with logs. So the first thing I'm going to do is divide both sides by 5, and that will cancel out the 5 in front of e to the 4x. So now I have that expression by itself, which is what I wanted. 95 divided by 5 is 19. And now I'm going to put this into logarithmic form. So remember, it would be e, that's my base, to the 19th equals 4x. But because this is, the base would be e, I'm going to do the natural log of 19 equals 4x. So first thing I'm going to do is figure out what the natural log of 19 is. And again, it's going to be a decimal. I'm going to round it to 4 decimal places. Equals 4x. And then I would divide both sides by 4. And I would come out that x equals 0.7361. All right, here's another one where we have to get the exponential expression isolated. So that would be 7 to the n. So I need to get rid of that 4. So what I'm going to do is divide both sides by 4. And I have 7 to the n equals, and then 148 divided by 4 is 37. Now I have my exponential expression isolated, so I can put it into logarithmic form. So here's my base, so it's going to be log base 7 of 37 equals n. Log base 7 of 37 equals n. So now all I have to do is type this into my calculator, one way or the other, and the answer that I will get is 1.8556. And again, I'm just rounding it to 4 decimal places because these are big, nasty decimals. So 4 decimal places is pretty much the standard. We're good there. Okay, so number 5. I have to get the exponential expression, which is 4 to the x plus 1, completely by itself. So the first thing I'm going to do here is I'm going to subtract 12. So I would have negative 4 to the x plus 1 equals 6. Now I want to get rid of that negative and put it on the other side. So I'm going to divide both sides by -1. So now I have positive 4 to the x plus 1 equals -6. So now I'm going to put this into logarithmic form. So log base 4 of -6 equals x plus 1. And then I would have to get x by itself. So I'm going to subtract 1 from both sides. So in a previous example, I calculated the decimal first. This is a different way. One thing I would be careful about is just making sure that you keep this log business separate from the -1. Now, this problem actually, it doesn't work. And the reason is because you can't take the log of a negative number. And I know we talked about that in lesson 2. So this -6 right here is the problem. So if you tried typing this into your calculator, so log base 4 of -6, your calculator is going to give you an error. So anytime that you're solving an equation and you end up with an error, this is going to give you a non-real answer, meaning that you can't solve it. So this is, I'm just going to write down here, non-real answer. We also did the empty set, meaning there's no solution to this problem. Okay, number 6. So before I can put this into logarithmic form, I need to get this thing that I just underlined in green by itself. The first thing I would have to do is add 8 to both sides. So that would give me 40 on the right, and I'd still have 5 times 10 to the 3k minus 3 on the left. Now I need to divide away that 5. So now I have 10 to the 3k minus 3 equals 8. And now I can put it into logarithmic form. So it's going to be log base 10 of 8 equals 3k minus 3. So remember, anytime that you have log base 10, that's the common logarithm, so I don't have to write the 10. I can just write log of 8 equals 3k minus 3. Now we're going to figure out what the log base 8 is. So if you put that in your calculator using the common log button, you get 0.9031, and that equals 3k minus 3. So now I'm going to add 3 to both sides, and that gives me 3.9031. And now I have to divide everything by 3. So my answer turns out to be 1.3010. All right, so to solve these equations, the first thing we want to do is isolate the logarithmic expression. So that's already done in this problem. We already have one logarithmic expression on the left side, and it equals something on the right side. So the next thing we need to do is put this into exponential form. So you can't see it here, but this is a common logarithm, so really the exponent there is 10. I'm sorry, the base is 10. So what we're going to do now is put this into exponential form. So it's going to be 10 to the second power equals x minus 4. And from here we can solve this just like a regular equation. So I have 10 squared is 100 equals x minus 4. And then I'm going to add 4 to both sides. So I get 104 equals x. So that is my answer. Okay, so I solved it. Now we need to check to make sure that it's in the domain. So that means if I plug this back in, is it going to give me a negative number that would give me an error in my calculator? So really quick, and we can do this kind of mentally from now on, but I want to show you how this works. So if I put in 104 minus 4 equals 2, so I replaced the x here with the answer that I got. So this would be log of 100 equals 2, and then if you wanted to check, you can either type in log of 100 into your calculator, or we can put it into exponential form and double check. I'm just going to say we put it into our calculator, and you get that 2 equals 2, so that means that this is not an extraneous solution. All right, so now let's try number 2. So I have to isolate the logarithmic expression. There's a 2 that I need to get rid of, so I'm going to divide it on both sides. And I'm left with log base 3 of 5x equals 4. At this point, I'm going to take this and put it into exponential form. So 3 to the 4th power equals 5x. 3 to the 4th power is 81. And then I would divide both sides by 5. And I would get that x is, you can either leave it as 81 over 5, or you can write it as the decimal 16.2. And then again, if you plugged in your x and you typed it into your calculator, you would see, so if I replaced this x with 16.2, and I typed in 2 log, I'll write it down, 2 log base 3 of 5 times 16.2, when you type this into your calculator, it's going to equal 8. And so then you'll know that this is the correct solution, and you do not have an extraneous solution. For problem 3, my logarithmic expression is already isolated. I have the natural log of 8x equals 2. So now I'm going to go straight to putting this into exponential form. So remember that anytime you have a natural log, the base is actually e. So I'm going to write e squared equals 8x. Okay, now e squared you can type into your calculator. It would give you 7.3891. And again, I'm rounding that to 4 decimal places because we can't possibly write down all of them. And so I have, 8x. So now I'm going to divide everything by 8. And my x, again, to 4 decimal places, would be 0.9236. Oops. Let me write this again. 0.9236. Okay, and again, if you plug this into your calculator, it would give you the right answer. So like if you typed in the natural log of 8 times 0.9236 into your calculator, it's going to give you approximately 2. It's not going to give you exactly 2 because we rounded our number, so it won't be exact, but it'll be very, very close to 2. All right, problem 4, I have to get the logarithmic expression by itself. That would be this right here. So that means I have to subtract this 1 to the other side. So I have log base 4 of 2x plus 5 equals 2. So now I can put this into exponential form. So I would have 4 squared equals 2x minus 5. 2x plus 5. 4 squared is 16. And then I would need to subtract 5 from both sides. So I would have 11 equals 2x, and then divide by 2. So you could write your answer in one of 2 ways. You could write x is 11 halves, or you could write x is 5.5. And then again, just to kind of double check, if you typed in log base 4 of 2 times 5.5 plus 5 plus 1, if you type that into your calculator, this one would give you exactly 3. And that would tell you that, not only was your answer correct, but it was not extraneous. All right, these last 2 examples are different than the first 4. We're going to be using a property of logarithms. And it's essentially the same thing we used when we talked about solving exponential equations in lesson 1. Once you get the 2 things to be the same on each side, so when we did exponentials, we were talking about getting the same base on both sides, so like 2 to the x plus 1 equals 2 cubed. Once we got the same base on each side, we could set their exponents equal to each other. Same thing is going to apply here, but now they have to be the same log with the same base on each side. Once you have that, then you can set whatever they're the log of, so the things in parentheses, you can set those equal to each other and solve. So both of these equations are set up so that we can automatically do that. If you look at number 5, both of these are common logs. That means they both have base 10. So even though I can't see it, I know that their logs, the base of their logs match. So now I can just take what's in the parentheses and set those equal to each other. And from here, I'm just solving this equation for x. So I would subtract 3x from both sides, and I'd have 2x minus 1 equals 5. And then I would add 1 to both sides. So I would have 2x equals 6. And then divide by 2, so x equals 3. Now again, we have to plug these numbers in and make sure that they not only work on both sides, but that they aren't giving us an extraneous solution. So if I plugged in 3, so 5 times 3 minus 1, and then I have to see if that works with 3 times 3 plus 5. So 5 times 3 minus 1, that would be 15 minus 1, or 14. And then this would be 9 plus 5, which is also 14. So I get the same thing on both sides. And it's not good enough actually for me just to say, oh, they're both came out to be the same. The reason I know that this is not extraneous is because I don't have a negative number here. So the number that's in the parentheses in your log cannot be negative, because negative numbers are not in the domain of logarithms. All right, number 6. So again, I have two common logarithms. That means they're both base 10. That means I can go straight to taking what's in the parentheses and setting them equal to each other. So I would subtract x first. So I would have x plus 15 equals negative 1, and then I would subtract 15 from both sides. So I would have x equals negative 16. So that would be my answer. And now I need to check it. So if I plug this one back in, so I would have log of 2 times negative 16 plus 15. And then I have log of negative 16 minus 1. All right, so this would turn out to be, let's see, that would be negative 32 plus 15. So that would be negative 17. And then negative 16 minus 1 is also log of negative 17. So you'll see that I did come out with the same thing on both sides. The catch is these numbers cannot be negative. If you type in log of negative 17 into your calculator, it's going to give you an error, meaning that it's not in the domain. So even though we came out with a solution for this problem, it's extraneous, meaning that even though we came out with we were able to solve it, it's extraneous, meaning it does not, the x value does not live in the domain of logarithms.